Okay, so before we dive into rational functions today, is there anything that you guys want to ask about or look at or whatnot? Well, that certainly sounds like you guys are thrilled and happy and content with everything at the moment. So yesterday we talked about the idea of rational numbers as being a number that can be written as a fraction of integers, and we think of integers as a fairly nice number set. And rational numbers are essentially the same thing. A rational number, as we talked about at the, a rational function, as we talked about yesterday, is a quotient of nice functions. And really our nicest function that we have is nice polynomials. So anything that can be written in the form p of x over q of x qualifies as what we're going to call a rational function. But some rational functions are essentially trivial and usually don't get the title rational functions. So for example, just x squared plus 3x minus 1. That technically is a rational function because it's x squared plus 3x minus 1 over 1. It's just 1 is such a boring polynomial. It's barely even considered a polynomial. It's a 0th degree polynomial. So in general, to be classified as a rational function, we need at least a first degree polynomial down here somewhere. So rational functions, that's an example of a fairly small rational function, a second degree polynomial divided by a first degree polynomial. Now, our most basic rational function, kind of the smallest thing that has all the components to be considered a rational function and nothing else, is good old 1 over x. The 1 in the numerator, again, it's still a rational function. It's still a polynomial. It's just as boring a polynomial as we can get. And the denominator is as small of a first degree polynomial as we could get. So that's our kind of small rational function. And ideally, we've played with the graph of 1 over x in your background somewhere, but just so we can take a look at it. This is what the graph of 1 over x looks like. And it's got some features that are classic for rational functions that we want to make sure that we look at because we're going to be trying to analyze rational functions in general today. So the couple of big things that we look at when we look at rational functions are the asymptotes that we're looking at here. And I want to talk a little bit about why those asymptotes happen. So let's consider this function 1 over x as x gets arbitrarily large and as x gets arbitrarily large negative. So as x goes to positive infinity and x goes to negative infinity, I want to look at that end behavior. What does the function do as x heads in those directions? Heads in those directions. So as opposed to our polynomials, for our polynomials, as our x got larger and larger, our polynomials went off towards either positive infinity or negative infinity. As this gets larger and larger, I mean, we could even get crazy large, then the kind of behavior of the function almost seems to disappear. But as we get to be larger and larger values for x, the value of the function gets smaller and smaller and smaller. So we're here at a x value of 1916, and this y scale is 1/2 up here, and it's the value of the function is almost indistinguishable from 0. Zoom in a lot further here. Okay, now we can get some distinction here. At 1916.01, our y value is about 0.0005, maybe 0.0006. So as that x is becoming large, the function is heading towards 0, and pretty dramatically. Frankly, we're out here near 2000. We didn't have to go anywhere near that far before we start seeing these small values. I mean, no, can't really go in very big chunks there. So that's, 1800-ish. We're still like just on that axis. So for these large values, large positive values anyway for x, we've got these very, very tiny outputs. And it happened pretty fast. Even at this is trying to be at 100, and that function value, I can tell you what the function value is. At 100, well, not surprisingly, at 100, we are 1/100th. That's because this function is giving us 1 over x. So as that x becomes larger and larger and larger, those y values get very, very small, very, very fast. So these are causing what we will generally refer to as it's causing a horizontal asymptote. This is a horizontal asymptote in the positive x direction. The graph is leveling off to, instead of positive infinity or negative infinity, it's leveling off at y equals 0. Now, if we look at x as we head towards negative infinity, it is doing exactly the same thing. Just instead of positive values, those are negative values. So it's heading towards 0 as it heads towards both positive infinity and negative infinity, making that nice horizontal asymptote in both directions at y equals 0. So this is a big quality that not only 1 over x has, but a lot of rational functions have. We often see them having this leveling off going on in our end behavior, as your book likes to say, our long run behavior. But there's more than that going on. If we look at what happens as the x heads toward 0, and we're going to start with heading toward 0 from the positive side. This is actually a standard notation for those of you going into calculus, as x heads towards 0 from the positive side. So as we come from the positive x values toward an x value of 0, I want to notice what happens to these values. We're taking that value and finding its reciprocal. Let me control that better with the mouse. So we get one nice number at 1, 1, but the reciprocal of 0.66 for an x is larger than 1. And as we take that reciprocal, those values for y, for the function, are going to start to get larger and larger and larger as we get closer and closer to 0. So similarly, if we look at what happens as our x values get super close to 0, we get larger and larger and larger values. Well, can't even hit them. Larger and larger values for, there we go, hit them for a second there. Larger and larger values for the function, because we're taking that very small number, 0.013, and finding its reciprocal, finding 1 over that value. So you can imagine, as we have 1 over some very tiny number, that's going to yield some really big, really large output. You can imagine 1 over 0.000001, some x value that's very close to 0. What's this function going to output? Well, 1 over that, well, 1 over that thing is 1 over, what is that? 10, 100,000, 10,000, 100,000, a million. So that's 1 over 1/1,000,000th is a million. So if we let our x input here be 1/1,000,000th, the function is outputting a million at that point, that very, very, very large value. So as we head toward 0, we start getting very, very large values for the function. And similarly, the other direction, as x heads towards 0 from the negative, we start going towards negative infinity. But what happens when we try to take this function and evaluate it at 0? We try to evaluate 1 over 0. And of course, we can't do that. 1 over 0 is undefined. Hence, at 0, if we tried to plug 0 into this function, there's nothing there. Zoom back in here. So at 0, this function has no output at all. There's not a y value associated with it. So just like we had a horizontal asymptote at y equals 0, we have a vertical asymptote here at x equals 0, not only because the function isn't defined at 0, but because as we get close to that 0, the function screeches off towards negative and or positive infinity, creating that asymptotic effect. So that's our basic 1 over x function. And the nice thing about it is it shows us that two of our big features. It shows us the possibility of these horizontal asymptotes, the flattening of the graph, and it shows us the possibility of these vertical asymptotes, this having the function try to get near somewhere where it's going to divide by 0 and kind of panic and rush off towards negative and positive infinity. But we certainly need to look at more robust versions of rational functions. But before we do that, any questions about any of that? That's kind of just a quick setup on what happens with 1 over x and what vertical and horizontal asymptotes look like, why they exist. You all happy with that so far? So let's look at some more robust examples. So how about y equals, let's go with x squared minus 2x minus 8 over x squared minus 9. So I want to look at that. If you guys want to bring up Desmos, if you've never used Desmos before, it's a good excuse to and play with some of your own functions, then that would be nice. Okay. So this rational function, it's still a rational function. It's a second degree polynomial over a second degree polynomial. By the way, the fact that the degrees match is going to be an important thing here for our function. So let's look at some of the results on what this thing is doing. If we look at our end behavior again, or long run behavior, as your book likes to call it, we're still getting that flattening effect. As the x values become large, and again, we could zoom way out, this thing flattens way out. For a large x value, imagine we put in an x value of, say, 100. That numerator is going to be 100 squared, which is 10,000. 10,000 minus 200 minus 8. That numerator is going to be about 10,000. Less by a couple hundred. This denominator, again, 100 squared is going to be 10,000. 10,000 minus 9 is about 10,000. So even just at x equals 100, this thing is going to be about 10,000 over 10,000. It's trying to be a 1. Well, does that look like what's happening in the graph? Does it look like as we head towards larger and larger x values, that function is heading towards a value of 1? Larger and larger x values, that function is trying to level off at 1. Now in this example, it won't ever reach that 1, but it's going to try, even in this direction. We put in those negative values. The squaring process makes them both positive. Okay, it's going to be a little more than 10,000 on top, a little bit less than 10,000 on the bottom, but it's still going to be trying to head towards 1 as we go off towards positive. So we still have a horizontal asymptote happening here, except this time the horizontal asymptote is happening at y equals 1 instead of y equals 0. And we'll have to talk about why. What about vertical asymptotes?
That'd be 3 and -3.
Well, yeah, if we look at the graph, it's having that same kind of panicky screech off towards negative and positive infinity happening, but instead of happening at 0 like it did before, it's happening at what definitely looks like +3 and what definitely looks like -3. So we still have vertical asymptotes, what looks like they just moved around. X equals 3 and x equals -3. So what about this function, this new one, is making that vertical asymptote or those vertical asymptotes happen at plus and -3 instead of happening at 0? Could we have looked at this function and predicted that based on something about its structure?
That'd be the denominator of the function, because that would be x plus 3 times x minus 3 if you factored it.
Mm-hmm.
How did we find 3? I'm sorry.
Oh, well, how he found 3 kind of depends on how he found 3. But visually on the graph, that value of, well, let me just put in there. That value at x equals 3, ooh, it's terrible. But visually it looked like at x equals 3, we have that of vertical asymptote.
Got it.
Fair?
Yes.
And at -3, it looks visually like the same thing is happening. And if we remember what caused the vertical asymptote before in 1 over x, it was the denominator trying to become that little tiny value. the denominator becoming a 0. Well, it's essentially the same thing that's happening here. When that denominator gets close to, when that x value gets close to 3, that 3 squared minus 9 is trying to become 0. It can never actually become 0 because at 0, the function would be undefined. But as it tries to get close to 0, those regular numbers of the numerator divided by those tiny numbers in the denominator are throwing out that positive infinity and that negative infinity. Fair? So as we get close to that -3, this thing's going to shoot out bigger and bigger and bigger values for y, as big as you want them to get. And as we head towards -3 from below, from the positive side, similarly, it wants to jump down there super fast. So what are we going to look for to try to identify where those vertical asymptotes are? As Andrew said, we're going to look at that denominator. Fair? Now, this one has some things that the other function didn't. This has a couple of pieces that the 1 over x didn't have. It has x-intercepts. It has an x-intercept right there. Can you guys see this cursor, right? I'm not just moving my cursor around and talking about it without being, okay. So there seems to be an x-intercept here and an x-intercept over here. Where are those, what values does it look like those x-intercepts are at?
Four and 2. 4 and -2.
4 and -2. So 4, 0, and -2, 0. So again, is there a way we could maybe if we didn't have the graph or weren't sure where those were, away from this graph, we could have figured out where those x-intercepts are?
From the numerator?
Well, what about the numerator?
Factor it.
If we factored it out, it would be x plus 2x minus 4.
So those x-intercepts seem to be coming from, to put it in our vocabulary, the zeros of our numerator, and those vertical asymptotes seem to be coming from the zeros of our denominator. Does that seem reasonable? When a value is trying to make this numerator 0, as we head towards x equals 4, when the numerator is 0, 0 divided by almost anything is 0. So when the numerator is 0, the whole thing wants to be 0. As we head towards x heads towards 3, notice I'm not saying equals 3 because it can't equal 3. As we head toward 3, this thing is becoming a very, very tiny number. That division is causing our infinite positive and negative infinite outputs, causing our vertical asymptotes to occur at positive and -3. So you guys very nicely went directly to factoring those. That actually gives us an option. We can really look at these functions in their factored form. We could just say, hey, let's look at a graph of that over that, x, let's say -1, x plus 2. Let's look at this in its factored form without having to come up with what that polynomial is, and see if that follows these same rules. Do you think it's going to follow those same guidelines?
Of course it does.
Of course it does. Oh, that's.
I mean, it has to, because it's the same thing as its multiplied polynomial form. It's the same.
And that numerator. Okay. So x plus 2. Well, the other ones, x minus 3. It's always fun to see the weird shapes that occur as you type stuff in, isn't it?
Yeah, one of them looked like a guy dancing.
So, first and foremost, is that what you thought that was going to look like? So there's a couple different things going on here than in the other one. Let's start with some of our, the questions that we've been asking here. If we tried to look at a horizontal asymptote, does this thing seem to have a horizontal asymptote? Does it seem to be leveling off somewhere? Or does it seem to be just getting larger and larger and larger and larger and larger?
Well, it looks like it's trying to level off at 0 in the middle.
But remember, our end behavior talks about what happens as the x's become large, right? As the x values become large, is this settling to some value? Or as the x values become large, are the outputs just getting larger and larger and larger?
It looks like a linear function.
It does kind of, and there's a reason for that. If we zoomed way out, you're absolutely right. This thing would look kind of like a line. Did I type that in weird? Explanation? No, okay, good. So it's behaving kind of like a linear function, and there is a reason for that, and we'll talk about that in a minute. So the horizontal asymptote, no, it lost it. But you are mentioning it does kind of look like a line. But really, horizontal asymptote lost horizontal asymptote. What about vertical asymptotes? Does it seem to have any?
Yeah, it's like a little bit above 0.
A little bit above 0. How much above 0?
Well, it looks more like 1 and some change now.
Well, let's see if we graphed x equals 1. So it looks like it's happening at 1, right? Well, any reason from looking at our function, any reason why it might have been at 1?
Because on the top and bottom of the function, x plus 2 would cancel out, right? Which leaves x minus 1 on the bottom.
Yeah, so this x minus 1 is causing a vertical asymptote, just like the denominator caused a vertical asymptote up here. But these x plus 2s, sort of, we do have to be careful. Those x plus 2s, because they match, they're keeping each other balanced. Fair? So as we head close to positive 1, this thing is behaving like our asymptote did before. It's causing a very small number in the denominator. That small number in the denominator multiplied by, as we head towards 1, this is going to be a 3. So as that little tiny number times 3, little tiny number times 3 is a little tiny number, gets divided by whatever this numerator is, we still get those eventually very, very, very large values coming out. We get that asymptotic effect. But what happens as we head toward x equals -2. Notice there's no vertical asymptote happening at -2. It doesn't look like anything happened at -2. Something did, though. Be careful. Let's say we put in even something like -1.9. Well, that value up there is going to become 0.9. That's going to become, what, -4.9. That's going to become our small 0.1 or 0.1. And we can make it a lot smaller if we wanted to. This is going to become the same 0.1, and that's going to become a -2.9. Notice what happens to those small values. That small value divided by this small value is going to become a 1, right? So the effect of this root down here, the effect of the factor of x plus 1 down here, is essentially being canceled out by the effect up here. So we're not getting that asymptotic effect because they're compensating for each other. They're balancing each other out. But this x minus 1 doesn't have a buddy on top, just like the x plus and minus 3 didn't have corresponding factors in the numerator. So when they tried to become close to 0, the division gave us a huge output. Here, as we get close to trying to make these factors zeros, they just keep canceling each other out and looking like they're not there. That seem reasonable? So it didn't cause the vertical asymptote. So our only vertical asymptote is occurring at the x equals 1, at the uncontrolled, unbalanced, unique factor in the denominator. Okay, what about x-intercepts? Where are our x-intercepts?
-1 and 3.
-1 and 3. Well, that is coming from our numerators, right? But why isn't there an x-intercept at the -2?
Same reason there wasn't an asymptote for the vertical.
Yeah, it's being canceled by this, right? But these didn't cause y-intercepts because they became, really tiny. They became y-intercepts because, or when they were 0. What happens to the function when this tries to be 0? When this tries to be a -2? Plus 2 is 0. This becomes 0, right? What happens when the denominator becomes 0? We're not defined. Now, I tell you what the problem is right now. And it comes with what you said, Andrew. You want to cancel those out, right?
Well, not necessarily cancel, just their effects on each other effectively cancel each other out. Because if it's like taking 4, multiplying it by 2, and then dividing it by 2, you still get 4.
True. So that x plus 2 over x plus 2, they're like multiplying by 4 and dividing by 4. And is there a number that you can't do that with, though? I know that's a weird question. These are always gonna, or look like they're always gonna kind of undo each other, and they're gonna divide out. The x plus 2 over x plus 2 is equal to 1, right? Ooh, I did not want that. Sorry. So is b divided by b always equal to 1? What's b over b equal to? It's a big question in calculus.
I think it is unless it's 0, right?
And that's the perfect answer, Aaron. This is equal to 1 only if b is not equal to 0. So the reason we can't just say, hey, I'm going to cancel these out is because they don't cancel at x equals -2. At x equals -2, this function's undefined. So what we don't see on this graph is a point right here at -2. And if I select it, notice the hole that is displayed on the graph. That hole is caused by the division by 0 error. This function essentially, as you've been saying, Andrew, essentially ignores the x plus 2 over x plus 2. It ignores those factors, except at -2, it can't ignore them because it causes an undefined point. It causes that hole to occur in the function. And we have to be careful because particularly on a computer or your calculators, it won't show it because that hole is infinitely small. We have to either ask what happens at that -2 or know by the structure of our function. There we go. Know by the structure of our function, because that factor is common in both the numerator and denominator, that hole must exist. By the way, this causes computer programs to crash all the time. You get this error where, the code will throw out this division by 0 error because somebody looked at their graph and said, oh, this graph is continuous in this region. And they forgot to check for holes.
Is that like an infinitesimally small gap in the line?
Yes, it is a measure 0 gap in the line.
Yeah, computers do not like dividing by 0.
No, they don't.
They also don't like a while loop that just says while true. Because it'll just continually think, yeah, while true, and it'll go over and over and over again until it just eats up all of its
Cache.
resources.
Yeah. So let's say we had, I don't want to use a 2 there, I want to use a 3 there. Let's say we had a function that was trying to behave nicely. This is more like our first problem. Not way up here, up here. Notice this one was nice because no copy of the numerator, no factor in the numerator was also in the denominator. We got into trouble with how this function looks as soon as we had that copy. Fair? So that's something we're going to have to watch out for. But if there's not a copy, the two things that we're going to look for are zeros of our numerator and zeros of our denominator. So that x plus 1 over x minus 2, that should give us x-intercepts, x plus 5 over, or times, sorry, x plus 3 should give us some vertical asymptotes. The question is, does it do that? Well, according to the rules that you guys suggested, what values make the numerator equal to 0?
-1 and 2.
-1 and 2. So does this thing have x-intercepts at -1 and 2? Seems to. -1 and 2. Okay, where's the denominator equal to 0?
-5 and -3.
-5 and -3. Does this thing have vertical asymptotes at -5 and -3? Does it look like? Looks like there was one there. Looks like there was one there. Crystal, does that seem more reasonable? Does this one seem to be leveling off, flattening out in its end behavior, unlike the last one?
I'm just confused as to what this whole little thing down beneath is doing.
This part down here?
Yeah.
Well, let's look. That little thing is happening between the -3 and the -5, right? So if we put in a value between -3 and -5, let's say -4, and want to evaluate this thing at -4, we would get -4 plus 1 times -4 minus 2 over -4 plus 5 times -4 plus 3. That numerator is going to be what? -3 times -6. And the denominator is going to be, this one's going to be a positive, and this one's going to be a negative, right? So that's going to give us a, what, 18 divided by -1. So we're going to get that nice -18. So in between those two asymptotes, this one's always going to be positive when we're between those two asymptotes. This one is always going to be negative when we're between those two asymptotes. Does that part make sense, Andrew? If we're between these two asymptotes at -3 and -5, the signs of those denominators are going to oscillate, making the denominator negative. When the denominator is negative, we get a part of the function value down here where the values are negative. When we are on either side of those asymptotes, if we went, say, -7, -7 would make this negative and that negative, making the denominator positive. When we're on the other side of the -3, both of these factors are going to be positive. So the only time their signs oscillate, giving a negative denominator and thus negative values for the function, happens in between those asymptotes. Hence the weird little jump down to the bottom and then the jump back up. The reason that those jumps are occurring is because at the -5, that factor switches from being positive to being negative. Does that seem reasonable? When that factor switches from positive to negative, the graph switches from heading up to heading down. Crystal, is that better? So let me ask you, if we had, say, x plus 1 over x minus 3, and it was just that. I don't even know why I have the parentheses there. I don't need them. If we asked, where is a vertical asymptote going to occur here, where might a vertical asymptote occur in the x plus 1 over x minus 3? Either Aaron, Crystal, or Ava. I've heard a bit from Justin and Andrew today. Or Dan, you have any thoughts? Where's the vertical asymptote possibly going to occur?
So it should occur at 3.
Vertical asymptotes happen when the denominator is 0, and I'm going to put a little parenthetical here, uncontrolled or unbalanced 0. So when the denominator is 0, happens at x equals 3, so we have at least the possibility of a vertical asymptote at x equals 3. If that also makes the numerator 0, we get that canceling effect and we get a hole. But there is no x minus 3 factor on top, so that is indeed going to make a vertical asymptote. What about x-intercepts? Where is the function itself going to be 0?
-1.
Yeah. The only way for this to equal 0 is for the numerator to equal 0. Again, as long as it doesn't also make the denominator 0. That -1 doesn't make the denominator equal to 0, so it is going to make an x-intercept. And if we graph that, we should see that. X plus 1, 12, over x minus 3. So we get a x-intercept at -1. Good. And we got that vertical asymptote occurring at x equals 3. Is that fair? You look skeptical of that, Crystal.
I can't conceptualize why any of this yet. Like, this was helpful for sure, but I'm just slowly lost on all of it.
Well, part of the reason this can get a little bit sticky is we're not, particularly with the vertical asymptotes, we're not talking about what happens at a value. We're talking about what happens near a value. And that always makes for a little bit weird of a conversation. Does that make sense?
A little bit.
But
So
go ahead.
we're really focused on like the x-axis, and when things go down or up, at what point of x that happens at? Is that what we're trying to conceptualize?
Yes, because our x is always our where. We're trying to look at where things happen.
Okay.
My question is, are these rules like rules that are going to stay, or do they have funky, like, at this, when it does this, this rule doesn't apply anymore?
They do, but the nice thing is we've already talked about those. Because if we try to make one that's not quite working, let's say x minus 3 times x plus 1 over x plus 1 times x plus 5. If we tried to ask, okay, where are the vertical asymptotes? One would be tempted to say at x equals -1 and x equals -5. And then where are our x-intercepts? One would be, again, tempted to say at x equals -1 and x equals 3.
But the -1s would cancel each other. Well, not cancel, but balance out. So really, it would just be the 5 and the 3, right?
Yeah, because the x plus 1s balance each other out, they're not actually going to create a vertical asymptote, and they're not actually going to create an x-intercept. What are they going to create instead?
0.
Well, a 0 in the numerator and the denominator. But what happens when you get a 0 in the numerator and the denominator?
Yeah, undefined.
You get undefined, and graphically you see a hole. So if we look at that, x plus 1 times, what was it, x minus 3? Divided by x plus 5. And, x plus 1. Well, what do we see? We see that y-intercept happening at, sorry, that x-intercept happening at x equals 3, just like we expected. We see a vertical asymptote at what looks like -5, and it is at -5. But at that -1, there's no x-intercept, and there's no vertical asymptote. But if we look, we'll find a hole at that location. So those are your caveats, Andrew. The rules work only when they work and then they don't. Zeros of the denominator cause vertical asymptotes when they are unique, when they're not copied in the numerator. Zeros of the numerator cause x-intercepts when they're not copied in the denominator. Those are the caveats.
That makes sense. It's just, it feels like every time we learn a concept, it's like, this is right, except for this.
Right. And that's one of the reasons I wanted to kind of lead with the excepts on this one, because we can't trust them until we almost until we have both. So often the first step for this process is figure out what the zeros of the denominator are, figure out what the zeros of the numerator are, and look. If anything is on both lists, it cancels out and makes a hole.
I take it this is why being able to factor complex polynomials is important.
Absolutely.
Prior to this?
Absolutely. Because you're usually not going to be handed these in their factored form. And we'll do a bunch of examples with that tomorrow. But one of the things I want to encourage you guys to do before kind of diving into this homework is, if you don't want to use Desmos and you want to use your calculator, you can do this same thing. But you can kind of just go through and put in different factors in these and look at what the graph is going to do. Or you can just go and put in, even different quadratics. They don't even have to be nice quadratics. The numbers should be fairly reasonable, just to keep everything happening in your screen. But notice this one. Okay, now we have the two vertical asymptotes occurring. There's one happening at -1 and happening at -5, because those are still the zeros of our denominator. But because we changed the numerator, x plus 1 is no longer a factor up there. So it's not being canceled out. How do I know it's not a factor? Because I can see the vertical asymptote. If x plus 1 was a factor, the vertical asymptote wouldn't be there. What are the zeros of x squared plus 3x plus 1? I don't know, but I'll tell you they're right here. 0.303 is a 0 of x squared plus 3x minus 1. How do I know that? Because it's an x-intercept. It's making the function 0. What's another one? -3.303. I bet you if we set that x squared plus 3x minus 1 equal to 0 and solved, that would be its decimal approximation. That seem reasonable? Ish. So, Crystal, I'm glad you like Desmos. You've mentioned that in the past, because one of the things we can do with Desmos is just plug in different things for these functions and look at what those results are and what that might tell us. Again, I've plugged in more random versions here, but if we took x squared minus 7 and set that equal to 0, we get plus or minus the square root of 7. Well, guess where those vertical asymptotes are occurring? At the square root of 7 and negative the square root of 7. The y-intercepts are occurring at the same place they did before because those are still the zeros of that numerator. Fair? Want to see something crazy before I let you go? Change that minus 7 into a plus 7. Where'd the vertical asymptotes go?
Why did that happen?
Well, when is x squared plus 7 equal to 0? It's never equal to 0. Well, technically, it's the square root of 7i, but that's not on our graph. Fair? So it's never dividing by 0, so it never has that panic effect happening of trying to divide by 0. If I put a plus, say, 6 there, now it doesn't even have it doesn't even have x-intercepts because x squared plus 3x plus 6 is never 0. It has no real zeros, no real zeros of the denominator. So there's no x-intercepts and there's no vertical asymptotes.
So are we going to get questions like this where we're going to have to figure out and then realize there's no zeros and then the answer is it's like not that
Oh, yeah.
fun?
So I encourage you to play with this. I would tend to recommend for a while, make sure what you're putting in the numerator and the denominator are factorable. That way you'll be able to see what you're looking at. But after a while, you should be able to just plug anything in there and have all kinds of fun stuff happening. Now, so far, with one exception, I've tried to make sure that these are the same degree, but notice this leveling off. This function still seems to want to level off at x equals 1. Sorry, not x equals 1, y equals 1. Y equals 1. It's still leveling off at that y equals 1. Well, what happens if we put a 5 in there and let's say a 3 down there? It's not leveling off at 1 anymore. Guess where it's leveling off to? It's leveling off at that 5/3. Hard to see with that particular example. So play with it. Throw in different values, throw in different functions. What happens if we make that a 3rd degree? We lost any sense of leveling off. 23 is not what I meant. I meant 3. There we go. More controlled. Went a little more crazy. But notice, again, no leveling off occurring. As it goes off in end behavior, it just shoots in both directions. What if that was a 4th power down there? Oh, okay, now it's leveling off again, but instead of leveling off at 1, it's leveling off at 0. Play with these things. Throw in different things and see the effect that they have. And tomorrow we'll try to bring it together and see if we can come to some nice, grand conclusions. Does that give you something to play with? And again, before I let you go, this thing certainly does seem to have what looks like 2 vertical asymptotes. Well, if we set that equal to 0 and solve, we're going to get a couple solutions. This looks like it doesn't have quite as many x-intercepts seems to have 1 there. Well, it's a third-degree polynomial. Third-degree polynomials have as many as 3 solutions, but sometimes they just have 1 solution. So maybe that's just the 1 solution to that polynomial. It'll all come together. It just takes some playing with. Questions about that before I let you go play with it? Funish, like, yeah, this is where stuff starts to happen. It's a little weird. And we are getting to the point that as we talk about asymptotes, those a word that we're avoiding or that I'm avoiding, and that word is limit. What is the limit of this function as we head towards -3? What is the limit of this function as we head towards positive infinity? What happens when we become infinitely close to something or infinitely far away from something? And that discussion about limit theory is where kind of calculus starts, because calculus is all about what happens when things become infinitely small, infinitely close, infinitely touchy. So this is part preparing you for that logic and that language. Okay, go play with this stuff and have a wonderful day.